will be ready to tap in 19 minutes. What's next?
402 killed fine grain, same as this one.
Okay. Metal here?
Yes?
What's the silicon?
120.
What's the manganese?
60.
Iron temperature, 2,500 degrees. You'll need 310,000 of hot metal, 135,000 of scrap, 30,000 of burnt lime, and 1,000 of spar.
Okay. Hot metal, man. We'll need 310,000 of hot metal for the next heat.
310,000? Okay.
Larry car operator, we need 30,000 lime, 1,000 spar for the next charge.
30,000 lime, 1,000 spar. Okay.
Scrap charger, we need 135,000 scrap for the next charge.
135,000 pounds of scrap.
Okay, next charge is all ready to go.
Okay, let's tap this one.
230-ton heats of high-quality steel in less than an hour, around the clock, 24 hours a day. This is basic oxygen steel making, newest, fastest, most efficient of all steel-making processes. As originally developed in Europe, the process was suitable only for limited production applications, 30 tons per heat. This was the first-generation basic oxygen furnace. Jones and Laughlin engineers built the first of the second-generation basic oxygen furnaces, known in the industry as BOFs. These are the 80-ton furnaces at Aliquippa. Successful production experience at Aliquippa made it possible to design and build the first of the third generation of BOFs, the 230-ton furnaces at Cleveland. The BOF process is entirely different from the open hearth. It requires no external fuel source to carry on the reaction. The vessel in which refining occurs is pear-shaped, open at the top. It is mounted on trunnions so it can tilt to receive its charge of scrap and hot metal. After it is charged, the furnace is returned to the upright position. Then an oxygen lance is lowered to a predetermined position over the bath. Oxygen roars through the lance at supersonic speed, 13,000 cubic feet per minute. As the carbon in the iron begins to react with the oxygen, carbon monoxide is generated. When it reaches the atmosphere at the mouth of the furnace, it burns to carbon dioxide, producing a brilliant orange flame. Soon after the oxygen blow begins, fluxing materials, principally burnt lime, are added. As oxidation proceeds, a liquid slag forms on the surface of the bath. Within about 15 minutes, the carbon content of the charge is down to about 2%. At 26 minutes, oxidation is complete. The carbon is down to the desired level, and the heat is ready to be tapped. Steel flows from the tap hole in the side of the furnace. The slag remains on top. When all of the steel has been tapped, the furnace is rotated to the other side and the slag is poured off. In the older, more costly open hearth process, even in the most up-to-date shops where oxygen is used to speed the reaction, The best heat time is several hours longer. When the decision was made to adapt the basic oxygen process to full-scale production, 230-ton heats with less than an hour between heats, a plant had to be designed that would accomplish miracles of materials handling. The production floor was engineered cleanly with plenty of space for easy, safe movement. Above the production floor, conveyor belts carry fluxing materials to storage bins. While one heat is in progress, the Larry car deposits flux for the next heat in a chute over the furnace. The heart of the operation is these two furnaces. Two because one can be relined and serviced while the other is operating. The operating furnace receives first its charge of scrap, brought by a self-propelled scrap charger of a special design. Hot metal arrives from the blast furnaces in a bottle car known as a submarine ladle. It pours its contents into the charging ladle, which rests on a scale that weighs the charge. The furnace tilts to receive the hot metal, brought by crane from the pouring platform. The water-cooled oxygen lance is lowered to a point above the surface of the bath, ready for the blow. In actual operation of the BOFs at J&L, electrostatic precipitators prevent smoke and fumes from entering the atmosphere. Inside the shop at Cleveland, basic oxygen steelmaking follows a split-second schedule. While one heat is in progress, the furnace charge for the next is made up. The secret is the computer developed by Jones and Laughlin research scientists. The general foreman feeds into the computer the composition and temperature of the hot metal, the desired tap temperature, and other process conditions. The computer calculates the amount of scrap, hot metal, and burnt lime. The melter orders the materials from the various stations.
135,000 pounds of scrap for the next charge.
Stewart, take out about 5,000. Okay.
Okay.
And the precise amount of burnt lime is discharged into the hopper above the furnace.
Flux is in the chute.
The molten iron, correct in weight and temperature, is poured from the submarine car into the charging ladle. The clock on the master control panel signals the start of the heat. Time, 11 o'clock. scrap charged in 1 minute and 40 seconds.
Pouring hot metal. Pouring hot metal.
At 3 minutes and 24 seconds, begin hot metal charge. Three minutes and 55 seconds. Hot metal charged. Prepare to lower lance.
On the hood. Bringing the lance down to 100.
Okay, bring her down. Take it slow. Hold it. You got it. 100 inches.
4 minutes and 39 seconds after we started to charge the furnace, the oxygen blow begins. During the course of the blow, the operator checks instruments that record the progress. The oxygen flow rate, the temperature of the cooling water. After 26 minutes, the blow comes to the end point. The flame changes intensity and color, signaling that oxidation has been completed. "27 minutes after the blow started, the oxygen is cut off and the lance is withdrawn. At the completion of the blow, workmen take the temperature of the steel.
Temperature 2,900. 2,900.
The steel is at the correct temperature and the order is given to tap it. 34 minutes and 8 seconds after the furnace charge began, the steel is tapped. just over 40 minutes from the beginning of the cycle, tapping is completed. This is basic oxygen furnace steel making, a triumph of engineering, research, and production know-how. The third generation BOF furnaces at Cleveland mark the beginning of a new era in steel making. But at Jones and Laughlin, engineering and research already are looking forward to the fourth and even the fifth generations. In an experimental furnace built to scale, scientists are studying furnace geometry, refractories, lance design, process changes. As furnace size increases, new problems of fluid dynamics, kinetics, and heat transfer are encountered and have to be solved. This miniature BOF duplicates the operating model even down to the recording dials. With it, Jones and Laughlin is working toward a better understanding of the process as a basis for improvements in the design of the furnace and for possible changes in the computer model. The results may lead to still more rapid refining of iron into steel in the operating BOFs, where steel making today is truly steel by stopwatch.